Today is October 8th, 2010. This is AP Calculus at Berkeley High School. And let's start looking at section 3.3, Rules for Differentiation. Okay, first of all, we're going to be talking about the derivative of a constant function. Now, I could just give you each of these rules and you just memorize them. But I would rather have each of these rules make sense. So let's talk about the constant function for just a second, and let's see if you can figure out what the rule is. All right? I'm going to put in a blank slide. A constant function looks like f of x is equal to some constant, and our book uses the letter A, B, C. Letters that are typically found in the first half of the alphabet are used for constants. Wow. What does that function look like? Okay, it's a line. What kind of line? A horizontal line. So if I go, I'd say up, and I declare this part to be A, my function looks like that. Are we good for there? Yeah. That's what the constant function looks like. Let's add in the stuff we already know. The derivative function is a function that returns a slope. Say that one more time.
This doesn't have a slope.
Does anyone want to confirm or refute that statement? This doesn't have a slope.
It's 0.
Lucy, the slope is 0. Discuss.
Because when you go, it's right on the left, so you go up 0 and over 7, 0 divided by any number is 0.
So, taking this example, if I go from this point to this point, and you want to say that this distance is 7, this would be a run of 7, but a rise of 0. Reaction?
If it's 0, I don't know. No, I don't have a reaction.
Well, one reaction would be, yes, you're right, I was wrong.
Okay.
Another one says, no, I'm still right, and the reason is...
I'm the homecoming king.
I dare say people who grade the AP exams have seen stranger answers.
That's good.
But they probably get the same number of points. So, Lucy, I think you nailed it. I think that this slope is a 0 slope. And I don't know if you've ever remembered the trick between remembering 0 slope versus no slope. Blue lines added in for influence.
I remember that.
So horizontal lines have 0 slope. Vertical lines have no slope.
So it's a 0.
Ah.
That is really nice. I've never heard
All right. So if that's the case, if f of x is equal to a, what does the f prime function look like? It looks like 0. So if f of x is a constant function, f prime of x is 0.
Yes.
All right? Great. I'm going to back up one slide. So, if f is a function with a constant value c, then f, or df dx, remember we don't say over for some reason, df dx, which is a synonym for the derivative with respect to x of the constant function c, is equal to 0. This is absolutely just another way of saying what we just found out. If it's in a yellow box, by the way, it means this is a direct quote from the book. This is one of those things that would be in a little box in one of the pages in the book. The derivative of every constant function is the 0 function, the function that always returns 0. What if the constant function is really big? A million. F of x is equal to a million.
0.
Still 0. Still a horizontal line, except it's a horizontal line at 1 million. I'm sorry, when I say 1 million, I'm supposed to say 1 million. Second rule. The derivative of a function in the form x to the nth uses a rule called the power rule. And this is for positive integers on the exponent. And the rule is that if I'm taking the derivative of x to the nth, the derivative is n times x to the n minus 1. So, the derivative of the x squared function is 2x. The derivative of the x cubed function, 3x squared. The derivative, if f of x is equal to x to the fourth, f prime is 4x cubed. Yes?
Would the derivative of cube root x be
Cube, well,
x to the, or 1/3 x?
there's two things I'm doing simultaneously right here, by the way. I want to reinforce the different ways that we can write about taking the derivative. If y is the cube root function, is that a positive?
Yeah.
Is that a positive integer power of x?
No.
Positive, yes. Integer, no. But we'll find out later that the derivative is still uses that same rule: 1/3 x to the negative 2/3 power. Why? Okay, the cube root of x is the same as x to the 1/3 power. All right. So if I take the power and I bring it down, there's your 1/3. What is 1/3 minus 1? Negative 2/3.
I told you this. Oh.
All right. Now, so Phil, my problem is that this is saying for positive integers, it ends up being true for that. There's only one really place that I need you to be wary of. The one place I need you to be wary of. And that has to do, this rule does not work with this function. Y is equal to
No, just 2. X to the negative 1.
no.
Absolute value.
Hold on, sorry. I'm blinking out here. Hold on. Well, wait. If I said, well, no. Tyler brought up x to the 0. We do know this one.
It's 1.
X to the 0 is 1. So y prime is equal to 0, because that's the constant function. We've already done that. No, I think we're okay. They want to only do positive integers because what they really would like us to do, or would like me to do at this point, is not just tell you what the rule is, but show you why the rule is true.
That might be me. Can I just check?
You can turn it off.
That's what I mean to do.
Okay. Hold on. Okay.
No, it's not me.
Is that you?
Mm-mm.
So,
Yeah.
but
'cause
turn
I
it,
forgot to
turn it
turn
off.
the phone
All right. So why is this rule true? And actually, the why of the rule true is why they want to limit us to positive integers at this moment. Does anyone have a reason why this is true? Why does this rule work?
Because it's been tested a million times.
Is that good enough? Is that how mathematicians work?
No, they tested a million times.
They test it a million times. That's how scientists work.
Oh, well, that's
They have a theory and they test it a bunch of times, and as long as it works out, it works out. That's how scientists work. That's not how mathematicians
Is
work.
this that one thing where it's like
There's no way to prove that it's
you
wrong.
prove it the one
That's the way to prove it's wrong, so therefore it's right.
They've proven it.
Sorry, that's how theologians work.
We did it in like last year.
Yeah, they proved it. You mean in
induction? Yes, mathematical induction.
Okay. The proof of this is not using mathematical induction. I'm going to go through a real quick proof of why this rule is. Are you ready?
Do we have to write this down?
It will be in the recording. If you feel the need to write it down later. Okay, ready? I'm going to take a function in the form x to the n. No, that's an n, believe it or not. It's a very scribbly n. If I start with the function f to the n, x to the n, how would I find its derivative?
nx to the n minus 1.
Wait, I thought we had this thing that said the derivative function is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That's what I thought we did when we wanted to find a derivative. Oh. All right. So if I really want to show it, not to say, oh, it happens to be that thing again and again and again, which is more how scientists work, or I can't prove that it's not true, which is how theologians work. No, it's Luke. All right. What I do is I start with my definitions. My definition of the derivative function is this limited function, right? Now, the limit as h approaches 0 of x plus h to the nth power minus x to the nth power all over h. Why is it n? Because that's what my original function is, Josh.
Yeah, I see it.
Right? So, typically when we've done these problems in the past, the next step is to expand that x plus h to the whatever things. All right? The expansion of this, and remember, n can be any positive integer.
Oh, this is good.
The expansion looks like this. The first term of that thing is x to the nth. The second term of that expanded binomial is n x to the x minus 1 h. Dot, dot, dot. And it goes all the way down until the last two terms are n x to the h n minus 1 plus the very last term of this expansion is h to the nth. And then, of course, we also have the negative x to the nth at the very end. And then this whole thing is over h. Are we okay with that idea? That would be the expansion. Then I switch from my red pen to my black pen, and what do? This is just like all the problems we've done in the past.
Cancel the x to the n.
You cancel these two terms out. And what we're left with is the limit as h approaches 0 of, what do we typically do?
Take the h out.
Take an h. Is it true that every single term in there has an h now?
Yeah.
So when I take the h out, I'm left with, that's the only h there, n x to the n minus 1 plus something blah, 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 and it's got an h, something blah, 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 and it's got an h squared, all the way, dot, 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 until my last term, which is h to the n minus 1. Remember, I took an h out of every single one of those terms. And then that whole thing is over h.
Cancel the
Now I can cancel the h's. And now that I canceled the h's, I can use the substitution process. All the h's go to 0. Well, the only thing that doesn't have an h is that. And that's our rule. Now, Phil, do you see how in this proof I had to assume that n was a positive integer, or this expansion doesn't work? That's why they presented it in the way they did, because that's the only way I can do a proof of this easily. It ends up being true otherwise, but I can't prove it right now. All right. So there's our power rule. And now we go on to the constant multiple rule. It says if we're taking the derivative of something in the form cu. Okay, by the way, there are certain conventions that our book uses. As I mentioned before, letters like A, B, C are considered constants. In our book, if you see one, you can just pretty much guess that that's going to be a constant. When we use the letter U, we use it as a function of x. U isn't a single variable. It's a stand-in for some function of x. This rule says that if I want to find the derivative of some constant times some function of x, it's equal to that constant times the derivative of that function. And this allows us to do a bunch more derivatives through the shortcut method. For example, if I ask what is the derivative with respect to x of 4x squared, this rule says this is equal to 4 times the derivative of x squared. And we have a rule to be able to do x squared, don't we? This is 4 times 2x, or 8x. There's one example problem. Hey, if y is equal to 3x to the 4th, I could think of that, the derivative of this is equal to 3 times whatever the derivative of x to the 4th is. Hey, x to the 4th. We can use the power rule again. 3 times 4x cubed, or 12x cubed. Yes?
Can you still use the second rule even if it has the constant multiple? Or no?
The second.
The second rule is the one that's like the power rule for positive integers.
No, because the power rule for positive integers says that to the nth, n has to be positive and an integer. 0 is not positive. So therefore we can't use it. Does it still work out? Yeah. All right. Any other examples you want to do of this? Okay, great. The sum and the difference rule. Remember I said a, b, and c are constants. U is a function of x. V is also a function of x. This is saying I'm taking the derivative of the sum or the difference of two functions of x. The rule says that the result of that derivative is the derivative of u with respect to x plus or minus the derivative of v with respect to x. Would you like to see this one in action? Yeah. Sure. I'm going to ask what is the derivative of x cubed plus x squared? This is acting like my u. U is a function of x. X cubed is a function of x. This is acting like my v. x squared is a function of x. This says, yeah, Billy, go ahead. Does everyone know the procedure? Yeah, you don't have to ask me. Just get your passbook, stamp yourself. If you have a phone, leave it. All right? This says I can treat this problem like the derivative of x cubed plus the derivative of x squared. Oh, once I break it down here, I have a rule for that. What is the derivative of x cubed? 3x squared. What is, and then a plus sign, and then what is the derivative of x squared? 2x. So now I can take big polynomials and I can take the derivatives because I can just break it up as lots of little derivatives. Let's do one more. What if y is 4x squared plus 2x minus 5?
Okay, but doable.
If I wanted to be very explicit about how I'm doing this,
Can't you factor?
I would break this down into 3 derivatives. I would break it down into 3 derivatives.
Kill 5.
Oh, sorry, bad notation.
Which is
Y prime would equal to the derivative of 4x squared plus the derivative of 2x plus the derivative of, minus the derivative of 5. What is the derivative of 4x squared?
8x.
8x. What is the derivative of 2x?
2.
And what is the derivative of 5?
0.
So, if I see something, I think a derivative is a big sum of difference expression, break it into smaller derivative problems. Now, by the way, I noticed that you didn't feel the need to break this into the constant multiplier rule.
Oh, yeah. I did.
In your head,
No, I
did you separate the 4 and say 4 times whatever the derivative of x squared is? Did you see this one? It said this is 2 times whatever the derivative of x is. All right. So there's the difference and the quotient rule. Why is it doing that? Because I didn't go through and make sure that this was.
It's just that the titles are.
The titles are too big. Okay. You can't see it really clearly, but all it's saying is y is equal to x to the 4th plus 2x squared minus 3/4 x minus 19. Let's find the derivative of that. How would we do that? Y prime is equal to the derivative with respect to x of x to the 4th plus 2 times the derivative of x squared minus 3/4 times the derivative of x minus the derivative of 19. I am being very explicit here, writing out every single step. What's going to happen? In 1 or 2 days' time, you're going to skip the explicit writing out step, and you're just going to go right to the answer. You're already there?
I'm already there.
Okay. So, what is our y prime then? 4x cubed
plus 2x.
plus
4x.
That's what
Wait,
I
what are we
mean.
looking at? Oh.
4x. Why 4? Because it's 2 times 2 times x. Yeah.
Do you have to break it up, or can you just do the second rule, 2x squared, and then just multiply the 2 by 2, and you get 4x? So, do you have to break it up?
I'm just showing it an explicit.
Okay, but you don't have to break it up.
Okay. I wrote it that way because if I explicitly want to say which rules did I use, I would say, oh, I'm using the sum and difference rule, to break it up there, I'm using the constant multiplier rule to pull them out. What's going to happen is all these things get internalized, and you just do it. All right? This next one, negative 3/4 times the derivative of x.
Minus 3/4.
Minus 3/4 because the derivative of x
Minus 0.
is 1, and then minus 0. And that's exactly what they got to.
Yeah.
Easy peasy?
Easy.
Okay.
If so,
Okay. I'm just gonna grab this function, and we're gonna do it on a blank sheet of paper. Plus or minus 8, minus 8x squared plus 2. Minus 8x squared plus 2. Okay. Now, here's where we start applying what derivatives mean. I've got this function, and I've got a question. This function may have some horizontal tangents. I'd like to find out where they are. Now, one way we could do this is to go right to the calculator. We could go right to the calculator and say, calculator, graph it out, show me where the horizontal tangents are. I think it was x to the 4th minus 8x squared plus 8
Plus 2.
plus 2.
Is it minus 8x squared or minus x squared?
Second, insert 8. Are we good? How about we go Zeus standard? I think we're missing some stuff here. I think we need to go a little bit further south. So how about window, and I'm going to adjust my x min to negative 20. How's that sound? I think we can go x max to 5. Let's look at the graph now. Okay, how could we find out where the horizontal tangents are just doing it graphically? Josh? Yep, looks like there's a horizontal tangent there. Can I find out exactly what the calculator thinks that is?
Yeah.
What's something called a minimum?
Yeah.
Second, calc, and minimum is option number 3. Philip, is that what you're going to say? All right. So in this way we say the left bound of this first minimum is over here, and then we got to get on the other side of the minimum. There's good. You never really do have to make a guess unless there's 2 minimums in there. Okay, and it looks like it's kind of close to negative 2. Maybe because there's a round off error with the calculator, maybe the answer really is negative 2. Maybe we reach a horizontal tangent when x is negative 2. Maybe? We can use minimum over here as well and get our, we think that's a good guess. We can go up to here and find a maximum. In fact, since I'm sort of already set up for this, a maximum and enter, boom, 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 boom. There, enter again. And they think that maximum is negative 6.7 times e to the, what the heck does that mean?
0.
It means it's essentially 0. It's a a number that's really, really close to 0. So it looks like negative 2, 0, and some other place. Now all of that is using the calculator graphically to make reasonably good estimates of where those horizontal tangents are. But can I show you a better way? Sure. Of course, I wouldn't ask that question unless the answer was yes. What is true about the slopes where horizontal tangents are?
0.
There's 0. can we get the slope equation out of this?
Yes.
Sure we can. Y prime is equal to 4x cubed minus 16x.
Yes.
I used what? The constant multiplier rule and the power rule and the addition, the sum and difference rule to do that, didn't I? Yes, I did. When does 4x cubed minus 16x equals 0? Because whenever x makes that expression 0, we have a horizontal tangent. How about we factor out a 4 and a x? And if I do that, I'm left with an x squared minus 4. 4x times x minus 2, x plus 2 equals 0. The roots of this equation are x equals 0, x equals 2, and x equals negative 2. So 0, not 6.7 times e to the negative 7. Sorry, 6.7 times 10 to the negative 7. Negative 2, not negative 0.000002. We're smart. We are smarter than the calculator. We are better than the calculator.
Yes.
And that's a typical question that we may ask. Okay. Next differentiation rule. Yes.
Will we be able to use our calculators on the test?
Some.
Half the test.
Well, sum has two definitions. One means the result of an addition. The other thing is not always. For example, on the AP exam, you have to realize the AP exam that you're going to take is broken into 4 parts. On 2 of the 4 parts, you may not use your calculators.
What about
Maybe. I have a couple of different options. I can either say, yes, you may, no, you may not, or I could say, I'm going to let you use your calculator on part of the exam, and then I will not let you use the calculator on another part. I have 3 different ways I can run it.
For the third one.
We'll have to see. We'll have to see. I have not made up my mind yet. All right. So, the product rule. If we have u and a v, remember what u and v stand for? Functions of x. If you have the product of 2 functions of x, their derivative is equal to u times the derivative of v plus v times the derivative of u. Now, I do not remember this rule in this form. But instead, I have a mantra, an expression that I repeat to myself every single time I do the product rule. Every single time I do the product rule, I say, first times the derivative of the second plus second times the derivative of the first. And if you listen to me when I'm doing calculus, I will say this every single time I do the product rule. Because you want to not think when you have to do this. You want it to be automatic. You want it to become second nature. You don't think about walking anymore. It just happens. I want that to happen for you for calculus as well. This is the kind of thing that you make this saying automatic in your mind. First times the root of the second, plus second times the root of the first. Next time you do it, you do this repeatedly, it becomes second nature. So, here's the product rule. Let's do a product rule with this particular function. And I'm going to do this on a separate sheet of paper. Whoops. Oops. What slide? Okay, there's our function that we're going to do an example of the product rule. Okay. Here's the second part of this problem. Ready? In order to do the product rule, you must be able to look at a function and realize that it's a product.
I see it.
You see it?
I see it.
You see it.
Oh yeah.
You see the product. You see the product of the first thing. What is the first thing in this case? X minus 4. What's the second thing? X squared plus 3. So we got to look at it and we see, I see that this function starts out as the product of two distinct functions. So when we go about finding the derivative of this, it's going to be the first times the derivative of the second. Plus the second times, I guess I don't really need a parenthesis there, times the derivative of the first. And now we're ready to do the derivatives, those two little derivatives, to get the answer. This is equal to 3, or x cubed minus 4 times, what is the derivative of x squared? 2x plus x squared plus 3. What is the derivative of x cubed minus 4? By the way, I'm going to finish this off by distributing these terms. X cubed times 2x is 2x to the 4th. 2x times negative 4 is negative 8x. X squared, 3x squared times x squared is 3x to the 4th. 3 times 3x squared is 9x squared. Do I have any common terms? Yeah, these two add up to what? 5x to the 4th plus 9x squared minus 8x. Now I do that because I'm going to do this problem again. You don't need to do it again. I'm going to just do it again. Why? Because I'm that way. Because it's fun. This is like eating bonbons. I do this for pleasure. Here's me doing the problem again. Before I take the derivative, I'm going to FOIL.
Very clever.
I didn't say you had to write this. This is just me doing it. This is what I do. X to the 3rd times x squared is x to the 5th. X cubed times 3 is 3x cubed. Negative 4 times x squared is negative 4x squared. Negative 4 times positive 3 is negative 12. Did I make any algebraic errors? No. In the FOIL? No? Okay. Based on that expanded polynomial, I'm going to take the derivative. The derivative of x to the 5th is 5x to the 4th. The derivative of 3x cubed is 9x squared. And the derivative of negative 4x squared is negative 8x. The derivative of 12 is 0. I'm not going to write it down. What's the crazy part? What's the... Ayana, tell me more.
I was just commenting.
No, I want to... your comment is right on point. I want it in the recording.
Oh, okay, recording. I think it's crazy that the one in the black took less of my pencil work than the one in the red.
It makes you wonder why we have a product rule, don't it?
It does.
Okay. And here's the reason why.
AP.
First of all,
Prove that.
no. This is bigger than the AP test. The reason why we have to do it. It's about calculus in general. All right. Yes, it took me less time to do it the second time, didn't it? Okay. What did I want you to leave this process with, though? Both methods gave me the same answer. All right. Now, the problem comes in is that we can't always distribute the two functions. We can't. Why?
Never mind.
No.
Never mind. I changed
It's a
my mind.
legitimate question. What if g of x is equal to x squared plus 1 times the sine of x?
Oh boy.
What pain.
We're screwed.
How do you do it?
Can't do
X
it.
squared sine x.
How do you do it?
Oh, I guess x squared times sine. Okay. That gives me x squared times sine x plus 1. I guess I could distribute that. Now, what are you going to do about that bad boy? That's a product.
That's 2x.
The derivative of one of it is 2x. We're
1 over x.
we're going to later find out what the derivative of sine of x is. It's cosine. Thank you. Okay. But it is still a product of two distinct functions of x, and we would still need to use the product rule in order to find that. So there are some cases where I could distribute, get the same answer, and it may seem like less work. But there are these other instances where we absolutely need this rule. And the rule is, again, first times the derivative of the second plus second times the derivative of the first. Internalize it. It is not a crime to talk to yourself while doing problems.
I do it all the time.
The quotient rule. Well, you knew it was coming. We've done powers, we've done adding and subtraction, we did multiplication. You knew it was coming. The quotient rule. So now our function is in the form u over v. What is u again? Some function of x. What is v? Some other function of x. Might even be the same function of x.
Could be.
The quotient rule says that the derivative of this function that's in the form u over v is equal to v times du dx minus u times dv dx all over v squared. You write it down in the symbol form. I'll write it down in the mantra form.
Yay.
Are you ready?
Yes.
This is what I repeat to myself every single time I do a quotient problem. Bottom times derivative of top minus top times derivative of bottom all over bottom squared. Bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. Yes. You know what? It's like for calculus, less than probably in calculus probably less than 10. In stats there was probably only 10 that we had. There wasn't more than 10.
What about in life?
In life, well, look both ways when you cross the street. Wear clean underwear in case you get hit by a truck. You know, there's all sorts of things that you have to remember to get through in life.
Is that like how it goes?
That was supposed to be a joke.
Oh.
All right. Okay. Are we ready to do an example of this kind of problem? This kind of mantra? Oh no, or squared plus 3. Okay, so there is our function. It's in the form of u over v. U is a function of x, v is a function of x. And we are asked to find the derivative. So f prime, I might even throw some extra notation in here just to be extra special cool. The derivative of f of x is equal to f prime of x, which is equal to bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Of course, we're not done yet because we have to take those two individual derivatives in order to get our final answer. X squared plus 3. And what is the derivative of x cubed minus 4? 3x squared minus, here's top, and what is the derivative of x squared plus 3? 2x all over x squared plus 3 squared. And now we got to distribute and clean it up. X squared times 3x squared is 3x to the 4th. 3 times 3x squared is 9x squared. Minus, and remember this is going to be minus everything that's a result of that second product. So minus 2x to the 4th minus 8x.
Negative 8x? Oh wait, never mind.
All over x squared plus 3. Now what do? Distribute the negative sign and look for like terms. It looks like we have a 3x to the 4th and a negative 2x to the 4th, giving me x to the 4th plus 9x squared plus 8x all over there. There's our final answer.
We don't have to do it.
Isn't that one?
Does it have an obvious factorization on the top? No. The bottom form is factored. We find it more.
Yeah, you can cancel out the x to the 4th.
Oh, I'm sorry. Yes, I could. Okay. There is an obvious factorization on the top. I can pull an x out. But I don't see the x cubed plus 9x plus 8 factoring any more than that.
It's x squared plus 3 not x squared.
On the bottom.
There's an x squared plus
Oh,
3.
I lost an x squared. That's a transcription error. And that's a problem with transcription. Okay? Are we good?
So much derivatives
So,
on Monday. It's a shortcut.
the power rule for negative integers of x. It's the same thing.
Is this the last one?
We're on slide 17 of 20, so almost.
So wait, so the 19th,
Wait, there's
20th
like
slide.
Well, so far we've done constant, power, sum and difference, product, quotient, negative. But look at the rule.
yeah.
Look at the rule.
The wire.
Oh, it's like the same.
Oh yeah.
It's the same as the power rule for positive.
Why aren't they just together?
Well, because at this point, I can actually show this to be true. Do you remember how I said, can I prove this to you, please? And then I proved it.
We don't need to do it again. It's okay.
Different proof.
I want to say
It's
the
a
same
different
answer.
proof.
Negatively the same answer.
It's a different proof. And it'll only take me, I'll be able to do it in the space provided. Are you ready? Here we go. Ready?
Yeah, I'm ready.
I would like to find out the derivative of a function in the form x to the n, where n is negative. I am going to change this problem into the derivative of x of 1 over x to the negative n.
Yeah, what is it?
Yeah, on the constant.
Time out. In this step, x is a negative number, right? N is negative. Negative. Yeah, good tip. That negative. All right. So, you know what? I see what's confusing you. I'm going to create a new variable for you to make things easier.
I'm okay that it's n.
Let m equal negative n. Are you okay with that? I create a new variable, call it m.
Just do that?
I used the magic word. Let.
Okay, I see. Okay.
I'm allowed to create new variables with the magic word let.
Godly.
Alright.
Not really.
Go some- Let's call it.
That's
No,
nice.
let's call it. Ready? Toddly.
He's got jokes.
Okay. Todd. Let's go with Todd-like. That's probably better. All right. So when I bring this thing down into the denominator of that fraction, it means to use the opposite of the exponent, right? We've done that. That's an algebraic rule. But I created this new variable, and this new variable says that wherever I see negative n, I can replace it with the letter m. Are you ready for this? 1 over x to the mth. Sorry if I spit on you. 1 over x to the mth is a quotient. There's a function of x on top. It happens to be the function 1, the constant function 1. There's a function on the bottom. I can now use the quotient rule on this derivative. And it is bottom times the derivative of the top. What is the derivative of a constant? 0. Minus the top. What is the derivative of x to the mth? M. And by the way, at this point, m is positive. M times x to the n minus 1 all over bottom square.
X to the 2m.
X to the 2m. All right? Let's clean this up. 0 times x to the mth. That just goes away. What does it give me now? It gives me negative 1 times, now there's an m here, and I've got an x to the m minus 1 and a 2m up there. See, which one's going to be, well, I'll tell you what, let's put it all in the upper part. That is equal to x to the m to the m minus 1 minus 2m. If I'm going to bring everything into the numerator, I take the exponent on the top and I subtract it by the exponent on the bottom.
Let's say m minus.
It's m minus 1 minus 2m.
And so now there's no denominator?
Now there's no denominator. I brought this guy up there, and I did the exponents to resolve that. Let me see if I can finish this off now. I got negative 1 times m, but what is negative? What is m? Negative n. So guess what negative m is? N.
But you can't do that yet.
Yeah, it gets rid of the negative one.
It's just n.
Oh, I'm sorry. I shouldn't have done that. M is negative n. Negative 1 times negative n. That's good. Can we clean up this exponent a little bit? What's
Negative m minus 1?
negative m minus 1? Because negative 2m plus an m is a negative
1.
m minus 1. Well, now my last step, negative 1 times negative n, n.
X to the n.
Okay, what is another way of, if m is equal to negative n, why can't I write, if m is negative n, what's another way of writing negative m? N.
Minus 1.
Look at that screw.
Wow.
Some crazy stuff right here.
That's amazing.
Is
Is that
It is proven. It's the end of the proof.
That means it's
It is proved. QED.
He said that we couldn't prove it because he
Nice.
couldn't.
All right, so now you can use this rule, which is the same as the old rule. But we proved it now.
Thank you.
All right, now we got
5 minutes.
5 minutes. We've got 2 slides.
He's gonna try. Going strong.
So, what about this function 1 over x?
Oh, I hate that function.
We could do this function. Yeah, we've done this problem in the limit form a bunch of times, and it's got a nasty fraction, and you got to find the common denominator. And I say no more. Woo! I say that function is x to the negative 1.
And then we can use the negative power rule.
And then I say the derivative then is going to be the negative power rule, which is the same old power rule, which is bring the power down
Hallelujah.
and reduce the power by 1. And when you go from negative 1, you reduce the power by 1, you go to negative 2, and that cleans up as negative 1 over x squared, which we have done this problem 15 times. No more using
No, I've done it
limits.
16 times.
Yay.
All right.
So happy I could be crying.
All right.
Wait, why?
This is a good place to stop.
Well, I
We're all
went
happy.
first, and then
Yes.
Charlie cut.
All right. Your assignment for over the weekend is... No, chain rule is in the next section. Actually, we don't introduce chain rule until section 3.6. So chain rule is not. You're not there yet. What is the chain rule? That's a very good question.
I'm reading about it tonight.
Okay. Your assign. No, it's not on the slide. Yep, we're going to write it on the board, so it's going to be in the movie. And your assignment is. This is from section 3.3. It's 1 through 41 odd. Hold on.
Kilometers. Kilometers.
53 through 58. All. But the 5 at the end are the AP review problems. So it's just like, it's just same old, same old. All right? Have a great weekend. Be safe at homecoming.
I'm going to be...
Yeah, we're still recording. No, but years from now, some archivist will come through, Fedor, the lost recording.